This is a short video about the beginning of chapter 2 from Stein's elementary number theory book. And we'll just do the first section for this video, but it's an intro to the ring of integers modulo n. And you've seen some of these before if you're coming out of the proofs class. Now, some of the things that modular arithmetic is going to do for us is it's going to allow us to do something like factor a 1,000 digit number, test whether a 1,000 digit number is prime without actually even factoring it. And another pretty surprising thing that we can do with modular arithmetic is, say, compute the last 1,000 digits of some gigantic multi-billion digit number like this power 1,234 raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 power. Pretty crazy. We can get the computer to do that for us. But the math that tells the computer how to do it is all based on modular arithmetic. So I'll scroll down a little bit. This is an overview of the whole chapter. We're just going to do the first part, about 2.1, congruence is modulo n. In this too, you'll be familiarized with maybe a little bit of modern algebra if you've had that. And it's right at the beginning, just what is a group and what is a ring? So these different algebraic structures that we have. So let's start with perhaps the simplest one of the two, which is a group. And so a group is the following. You have a set G, and there's an operation that you can do on G. And in our case, we usually sometimes denote it by multiplication, as you see here. It looks like I'm multiplying three elements of G together, but don't be fooled that it has to be multiplication all the time. We could do addition, and you'll see in a little bit. So what should we have? I should have a set where it makes sense to do some kind of operation to the elements in that set, and there should be an identity in the element, or then an identity element in that set. So here are the properties that this should have. So I should have this associative property here. I should be able to place parentheses wherever I want and get the same result when I do the group operation. And the other thing is really 2 for 1, number 2 here. For each element in my set, I should have this 1 here should truly be an identity. So 1 applied to A should be the same as A applied to 1, should just give me A back. So it's kind of like multiplication by 1. The notation is very suggestive. And the last thing we should also have for a group is that there should exist an elements of the group that more or less undoes multiplication by A. So in other words, every element should have an inverse. So before we move on to the next definition, what you might think about is sort of a poster child for what a group is the integers with the operation of addition. So this would be my group G here. And so what's going on when I add two integers together, or when I add any three integers together, I know that it doesn't matter how I group them. Like A plus B, then plus C is the same thing as A, then plus B plus C. And then similarly, the identity in this group is 0 is the identity. And it's a little bit different, like I wouldn't call it 1, because A plus 0 gives me back A, which is the same thing as 0 plus A. So I have an element that doesn't change any other element when they're applied to each other. And then the last thing I should have that happens is that if A is an integer, then minus A is its inverse, because A plus negative A, when I do the group operation to these two elements, I get the identity back, which is what this is trying to say. It's a little bit tricky, but think about maybe more generally about using, don't get too tied to multiplication. It doesn't really matter what operation it actually is. So the integers are maybe your poster child again for what a group should be. The integers are pretty nice as well because the operation of addition itself, A plus B, is the same thing as B plus A. This property, this commutativity that we take for granted, right? It's not necessarily a requirement for a group. So we'll call a group where the commutative property is satisfied, we'll call it a abelian. We will normally stick to abelian groups in this class. Non-abelian groups, if you're interested, are, say, square matrices of the same size with the operation of multiplication. That's a very common non-abelian group. But if you're not interested in looking further in that, you can ignore it. So again, one more time, a group is a set that has one operation with these properties here. Now, what if I added another operation to the set? So then we'll get a ring. And so the second operation that I add to the set has to satisfy some properties as well. So a ring is a set R with two operations. We'll denote them by plus and times. And again, it's kind of because the integers, it's kind of our poster child for what a ring should be. And it should have two elements, 0 and 1, which, as you probably guess, would serve as an additive identity and a multiplicative identity, such that the following things should happen. So R should totally be an abelian group under one of the operations. We'll say under addition. And now the multiplication operation isn't as stringent. The properties aren't as stringent. So what we should have is that there should be a multiplicative identity, and the multiplicative operation should be associative. But in particular, what I don't require is I don't require multiplication to satisfy or be closed under inverses. So I don't require there to be some number b such that a times b gives me back 1. So that's the difference. And the last thing, how do the operations of addition and multiplication play with each other in the set? You should have the distributive property. Now for a ring, if the multiplication operation is commutative, then we'd call the ring a commutative ring. And the same thing here, again, the ring of, say, 2 by 2 matrices, where you add them the normal way, if you know how to do that, and you multiply the normal way, that forms a ring that's non-abelian, is non-commutative. But again, the integers, if you think about, if I have the integers are kind of going to be our poster child for a ring, where I've got the operation of addition, where I know that that's an abelian group, and I also got the operation of multiplication, and multiplication satisfies all these properties here. And what I was trying to say earlier is it's okay that 2 times what gives me 1? Well, this number would have to be 1/2, which is not an element of z. But we're not bothered by that. We don't require having to have multiplicative inverses to be a ring. So a ring just has that extra bit of structure. Now, the main ring that we're going to work on is the ring of integers mod n. If you're coming out of the proofs class, you're probably more used to just denoting that by z with a subscript of n. It's the exact same thing, just the notation we use in this class is going to be a little bit more different. And remember, how is this ring defined? It's the set of all these equivalence classes where we're going to say that two integers a and b are congruent to each other modulo n if n divides their difference. And the notation for it, one notation for it is a is equivalent to b modulo n. Now the book throws in some modern algebra terminology. So nz is a common way to denote the ideal generated by the number n. So it just consists of all the multiples of n. We might use the terminology ideal, but for now, just think about that as denoting all the multiples of n. Now, another thing that maybe we did in the proofs class was in Zn, it was very typical for us to denote the elements with these kind of brackets, where bracket A denoted the equivalence class of the number A. What we're going to do instead for us, since we use this notation Z mod nz, the elements in this ring will look like A plus that denominator. So this is the same thing as what we used earlier with this. And so I hope that it makes more sense now. Maybe you recall from the proofs class, how do you add, say, A plus B? How do you add two equivalence classes to each other? You just add the representatives, A plus B. And what is this trying to say to do? This is saying exactly that, just in a slightly different language with different notation. So this says to add two elements of this ring, just add the representatives. So notice this nz is just going to always be tacked on at the end. It's just notation. Similarly, how do you multiply two equivalence classes together? You multiply them again, it looks like, just by multiplying the representatives. And again, adding this notation at the very end. It's just standard, it's always going to be there, plus nz. So to give you an example, z mod 3z, which I'll just keep saying it for a little bit, same thing as z sub 3, if you will, or z3. It should have three equivalence classes in it. These are all the numbers that are equivalent to 0 mod 3. In other words, all the numbers divisible by 3. These are all the numbers who have a remainder of 1 when divided by 3. And then the last equivalence class is all the numbers who have a remainder of 2 when divided by 3. So those are our equivalence classes. So how you might write these elements, they wrote them in this as these elements are sets themselves. And remember, it's more convenient maybe for us to say this would be 3z, this would be 1 plus 3z, and this would be, say, 2 plus 3z. So I could think of this ring as having these three elements. Similarly, Sage can do some of this stuff for you. So you can tell Sage that I'm going to play with the ring of integers mod 3. I can list the elements here, and it should spit those out. And what I'd like to do is go to Sage and just show you something kind of similar. So if I said R is equal to, integers 5, say, and let's do list R, and it spits out 0, 1, 2, 3, 4. And I can also do like modular arithmetic. So what do we take for granted? I know that 3 plus 4 is 7, but the remainder when divided by 5 is 2. So I expect 3 plus 4 to be 2 in this ring. So if I do R' parentheses 3 plus r parentheses 4, I expect it to spit out 2, and it does. Another way to do that, by the way, is Sage can do like modular arithmetic. The notation for it is a percent sign. So if I did 3 plus 4, and then if I put percent 5, that you should read that as this is, reduce 3 plus 4 mod 5, right? See what the remainder is when you divide by 5. So that percent sign is what does it. So if I do that, that's another way to get 2. So you can use either way to do modular arithmetic. So let me go back to my note. And again, we say a little bit more about the word ideal here, but for us, just think about it. Think about this as being the set of all multiples of n. And let me tell you about another structure. So far you've got a group, you've got a ring. A special kind of ring is called a field. And a field is a ring where every non-zero element does have a multiplicative inverse. So some common rings that we're maybe used to are like the real numbers, or the rational numbers, or the complex numbers. One that we might not be as used to, but you might remember from a proofs class, is whenever n is prime, which we'll use p to denote it then this is a field. So the ring that we're used to. So something like z3, which was 1 plus, it's just 3z, 1 plus 3z, and 2 plus 3z, that constitutes a field as well. So in particular, maybe you see, if you multiply 2 plus 3z by itself, that would give you 4 plus 3z, but that 4 is equivalent to 1. So in other words, that gives you back the identity. So that element is its own inverse. Therefore, every non-zero element, how should you think of 0 in this ring, by the way? 3z would be like the 0 of this ring. When I add 3z to another element, this is the same thing as 0 plus 3z. So say when I add 0 plus 3z and 1 plus 3z, remember you just add the 0 and the 1. So that just gives you this element back. So anyway, z3 is a good example of a field. And more generally, whenever p is a prime, z mod pz is a field, or zp is a field if you still like that. The second to last thing in this section is the relationship between the integers and, say, the integers mod n. What's maybe a connection between these two rings? And remember, that's what, say, homomorphisms were for if you took modern algebra. But you could just think of it, say, as some kind of a function or a map. Map and function, will use those kind of interchangeably. So the point is, you've got some kind of a map that tells you that when you plug in an integer, f of a, it should spit out the equivalence class of a, which again, we're just denoting by this, a plus nc. So that's called the reduction map. You plug in an integer, it spits out a reduced mod n, and that's what this says in an equation. And we can also go backwards. If you've got an equivalence class, we have what's called a lift, and the lift is just what's that representative. And so how you should read this then, a is a lift of this equivalence class, a plus nz. So if I go scroll back up here a little bit, I could say that 4 is a lift of 1 plus 3z, since 4 is in that equivalence class with 1. Similarly, I could say that negative 1 is a lift of 2 plus 3z here, since negative 1 is in that equivalence class. So I hope that you're a little bit more comfortable with, again, arithmetic and z mod nz. And maybe a result that's kind of fun to do. Modular arithmetic tells me an awful lot about divisibility of integers. And so that's why this relationship between the integers and z mod nz is very important. This ring offers a lot of information about divisibility in this ring. And so to give you an example of such a thing here, any number, any integer that's divisible by 3, well, it's only divisible by 3 if and only if the sum of the digits is divisible by 3. So how would you do such a thing here? Well, I could write n out in sort of its base 10 expansion. So I've got a plus whatever 10 times b is, plus whatever 100 times c is, where a, b, and c are the digits of this number. Now, what we're going to do, I care about things being divisible by 3. Let's think about 10 is equivalent to 1 mod 3. So in other words, the remainder, when you divide 10 by 3, is 1, is what that says. So what can we do? Well, if 10 is equivalent to 1 mod 3, so are all the powers of 10. And that's exactly what we're going to do. When I reduce this mod 3, all these powers of 10 become 1. So in that case, n should be equivalent to just the sum of its digits. And in that case, what do we have then? I have that the sum of its digits, if n is divisible by 3, then the sum of its digits have to be divisible by 3. And so that is, again, the meat of the proposition.